Well, in our previous class, we had started the case studies of phase diagrams. Case studies means we take examples and try to understand the concepts behind the principles. Now, the water system was the first example we looked at. In fact, water system is an one component three phase system. And since we have seen all the phases, we have we need not have to uh, see the phases of water in a chemical laboratory, right? Water is everywhere. We have seen ice, we have seen vapors, we have seen liquids. So the understanding of water system was a bit easier. From now onwards, we take up some systems which are unique in their own ways and understand the phase diagrams of those systems. And basically, to remind you again, what is the uh, main importance of the phase diagram? That if you give the values of pressure and temperature, looking at the phase diagram, you can tell at that temperature and at that pressure which phase of the system exists. Is it not? For example, if we go back to water, if I tell you at 140 degrees Celsius at 1 atmospheric pressure, which phase of the water exists? Only the vapor phase. Is it not? Like that. Now we will go on to a bit complicated system, that is the sulfur system. But what are the similarities of sulfur system with water? Like water, sulfur is also one component system. What do we mean by a one component system? It is a single chemical entity which is there in all phases. In water system, the entity was H2O. That's the compound which was there in all phases. Similarly, in sulfur, it is sulfur which is there in all phases. Okay, fine. But how many phases were there for water? Three phases. But for sulfur, there are four phases. In fact, uh, for a given compound, existence of three phases can be readily perceived. Why? It can exist as a solid, it can exist as a liquid, it can exist as vapor. Is it not? Okay. Which is this additional phase then in the sulfur? That is the different phases or two phases within the solid state. Okay. Hope you have heard of or you may be studying crystal structures in your uh, chemistry syllabus, and you have heard of this word called polymorphism in crystals. What do we mean by polymorphism? The same compound exists in different crystal structures. That is called polymorphism. Same thing happens to sulfur also. In the solid sulfur, we don't have all solid sulfur in a single phase. Depending upon the temperature and pressure, sulfur can change its crystal structure. Okay. So there are two phases identified for solid sulfur. One is the rhombic sulfur, the other is the monoclinic sulfur. And please don't worry too much about the structures of rhombic sulfur and monoclinic sulfur, because in this chapter phase diagram, all that we are looking into is two different phases of solid sulfur are there. One is the rhombic sulfur and the other is the monoclinic sulfur. Okay, fine. So now counting these two phases, what are the total number of phases possible? Four phases. Rhombic sulfur, monoclinic sulfur, and both are solids. Please remember, both are solids, rhombic and monoclinic. In fact, the different phases amongst the different phases within a state of matter, like liquid, gas, solid, is largely observed in the solid phase, because uh, there are examples, many examples, where a single compound can exist in different solids. We take allotropic forms of carbon example. Carbon element exists in how many solid forms? How many allotropic forms? It can be a diamond, it is a solid. It can be a coal, solid. Charcoal, solid. Graphite, solid. So all these 3, 4, 5 are different phases of carbon itself. Okay, fine. So they are polymorphs, of course. Since all the phases are not crystalline there, we don't call them polymorphs. There are amorphous phase also, except diamond is crystalline. But in case of sulfur, they are crystalline. Therefore, we call rhombic sulfur, we call monoclinic sulfur. Okay, fine. Now, of course, before we see the phase diagram of sulfur, let us see the phases first. As I told you, to talk about water, it was easier because you have seen all the phases of water. But sulfur, okay, How is the rhombic sulfur? How is the monoclinic sulfur? Look at this picture. Can you see the difference in the solid of the sulfur? The left one is the rhombic sulfur and the other is the monoclinic sulfur. The rhombic sulfur, the word would have come from a rhombus shape of the crystals. Whereas the monoclinic sulfur, the crystals are needle shaped, long, elongated needle shaped. What about the rhombic sulfur? They are polyhedron, rhombus shaped. So if I give you a sulfur solid, you can tell me whether it is rhombic or monoclinic based on their appearance itself. Is it not? So this is what I told. This is what polymorphism is. The same crystal is existing in many different crystalline forms. Not same crystal, same solid, same compound is existing in many different crystalline forms. That is what. So in fact, in few cases, the difference would be very subtle, in the sense that you have to visualize that under a microscope to see a difference. But in case of sulfur, it's straightforward, very straightforward. It is very obvious, conspicuous. You can see it yourself, rhombic and monoclinic. So now we have to consider these two phases also. This is only a graphical representation, rhombic and monoclinic. So at what degree Celsius, what temperature the rhombic becomes monoclinic? 96 degrees Celsius. This is called transition point of sulfur. That means above 96 degrees Celsius, monoclinic sulfur exists. Below 96, rhombic sulfur exists. This can also be found on the phase diagram. At 96 degrees Celsius, you would have a phase transition. Okay. Of course, this is for 1 atmospheric pressure. You have a phase transition at 96 degrees Celsius. This is evident on the phase diagram also. Okay. And liquid sulfur is really a very colorful liquid. Yeah, it's red in color, liquid sulfur. Okay, fine. And of course, sulfur vapors, they are sulfur fumes. Maybe you have seen sulfur vapor. Sometimes the sulfur vapors come out of the earth's vents. What do you mean by that? There are some cracks or vents on the fissures on the earth surface. In some part of the world, the sulfur vapors are given out, exhausted from those vents, sulfur vapors. Okay. So now we'll go into the phase diagram of sulfur. So this is a simplified version of the phase diagram. You can see in this phase diagram, basically what is a phase diagram? It is a graph of pressure and temperature. Of course, anyways, when we take up two component system, I will explain this concept. Sometimes a third dimension is also required, three-dimensional phase diagrams. Anyway, for this it is only two-dimensional because there are only two variables, pressure and temperature. Composition is not under consideration because this is one component system. See, in your phase rule, how many variables are there? F, C, and P. Okay, plus 2. And what is that 2? 2 is, one is pressure, one is temperature. These are the two variables. In fact, we derived the phase rule also using this argument. Plus 2 means one is pressure and the other is temperature. But for many systems, apart from pressure and temperature, the composition of the phase is also a variable. Okay, so that has to be plotted in a three-dimensional form. Anyways, that we will talk about later, how to reduce that in condensed phase diagrams, all those things. Now, for this, you look at this graph, it is very clear. Now, what are the major elements or major features of this phase diagram? You can see four phases: rhombic, monoclinic, liquid, and vapor, gaseous, sulfur. Those four phases. And in fact, you also have demarcations at what temperature. For example, at 1 atmospheric pressure, let us consider 1 atmospheric pressure. So what is 1 atmosphere in case of pascals? It is 101 kilopascals. 1 atmospheric pressure between or till, what is this temperature? What is this temperature? 1 atmospheric pressure. What is this temperature? 114 degrees Celsius. Is it not? So below 114 degrees Celsius at 1 atmospheric pressure, you have only rhombic sulfur. Above 114, you have monoclinics. So see, Constructing phase diagram isn't very difficult. All that you have to do is heating and cooling experiments. You take sulfur, rhombic sulfur example, and fix a pressure value. Most of the times we work at 1 atmospheric pressure. Is it not? Of course, higher pressure values are also important or also significant. But now, as a beginners, if we look at, we are working at 1 atmospheric pressure. Start heating sulfur till 114 degrees Celsius, it will be rhombic sulfur. After 114 degrees Celsius, it will transit into, or it will change into monoclinic sulfur. And after 119 degrees Celsius, it will become liquid. And liquid 445 degrees Celsius, it will become vapor. Are you understanding? So it is straightforward. At 1 atmosphere, what are the different phases at different temperatures? You can construct a phase diagram like this by varying the pressure. Now at pressures lower than 1 atmosphere, what happens? Phases exist and the range of their existence, temperature range is changed. Is it not? So how to example here at an atmosphere of 5 into 10 to the power of -4 atmospheres, the rhombic sulfur exists not till 114 degrees Celsius, much lower than 114 degrees Celsius. After this, monoclinic sulfur will start. And then, anyways, we get a triple point here. Don't worry. So now, so how to basically, what is the basic protocol for constructing a phase diagram? It is easy. You just have to go on heating or cooling the given compound and see at different temperatures what are the phases existing. Plot it on a graph and join all the dots and do it for many pressure values. Join all the dots, you will get the phase diagram of the system. Okay, okay, fine. Fine. This is a bit not that visually attractive. It is more technical and more detailed phase. Not that detailed, reasonably more detailed than the previous one. Is it not? Here I was just showing you the phase diagram, different phases. In fact, looking at this, you can straight away tell there are 4 areas in this phase diagram. Is it? See, in any phase diagram, if I give you, all the thing you have to write about that phase diagram is first how many curves, how many areas, how many triple points. That's all. If you describe all these things, essentially you are describing a phase diagram of any system. So how many areas at least? 1, 2, 3, 4. Is it not? Because these 4 areas correspond to 4 different phases of sulfur. Okay, fine. This is a bit detailed explanation. You see here, at 1 atmospheric pressure, maybe this is not very okay. At 1 atmospheric pressure, say this. This is rhombic sulfur, monoclinic sulfur, liquid, and the gas. How is this more detailed? Because it gives you the values of temperature and pressure for different transitions. Now, as I told you that we are working at 1 atmospheric pressure mostly. So at 1 atmospheric pressure, see this, till 95.96 degrees Celsius, you have monoclinic sulfur. I'm sorry that in this it has come out like till 1 atmosphere, at 1 atmosphere, till 114 the rhombic sulfur exists. It is wrong. Okay, this is correct. At 1 atmospheric pressure, till 95 degrees Celsius or 95.39, 95.4 degrees Celsius, rhombic sulfur exists. Is it not? This is the area of rhombic sulfur. After 95.39, monoclinic sulfur starts. At 115 degrees Celsius, vapor melting starts. Okay, so melting starts. At 440 degrees Celsius, 44 degrees Celsius, vaporization starts. Okay, so if you can label these transitions, you can pin it with its temperature. You are essentially telling about the melting points and the freezing points. Is it not? What is this point called? This is a transition point between rhombic and monoclinic sulfur. This is not melting. This is not freezing, because one crystalline form is getting converted to another crystalline form. So this is called a transition point. So this is transition point. Now, what is the temperature of transition at 1 atmosphere? Anyways, we are talking about 1 atmosphere. Is 95.39 degrees Celsius. And what is this point where sulfur is becoming liquid? Is the melting point of sulfur. So now at 1 atmosphere, which is the phase which is melting? It is always monoclinic. It is the monoclinic phase which is melting. Is it not? You cannot have rhombic phase which is melting, because as you eat rhombic, it converts to monoclinic and then melts at 115 degrees Celsius. And see, look at the temperature range for the existence of liquid sulfur here. It is 115 degrees Celsius to 444 degrees Celsius at 1 atmospheric pressure. Such a huge range, almost about 350 degrees, 325 degrees Celsius. The sulfur remains as liquid. Sulfur remains as liquid. And then later at 444.6 degrees Celsius, this is the boiling point of sulfur. The liquid sulfur converts into vapor. Okay, fine. So I will show you the next diagram. Phase diagram is nothing but the same phase diagram, but the curves are labeled. Okay, see this. Curves are labeled. Maybe this is easier. This is a bit detailed. AB is the curve, BE, BC, CD, CE. The curves are labeled. Okay, fine. So what are the additional features in this diagram compared to this diagram, except the labeling? Of course, the first point is the curves are labeled. The second point is this. Can you see these dotted lines here? Can you see these dotted lines? Dotted lines, dotted lines, dotted lines. These dotted lines are not here. Okay. So what are these dotted lines basically? Why does the dotted line come? Okay. See, anyway, I'll explain that. These dotted lines correspond to metastable equilibrium. That metastable equilibrium is not shown in this phase diagram. What are metastable equilibria? What is metastable equilibrium? That we will understand later. So, what are the features of the phase diagram? The elements of the phase diagram which we have to describe. There are 6 curves: A, B, B, C, C, D, B, E, C, E, and E. And there are 3 triple points. Please remember, water system had only one triple point, whereas sulfur system has 3 triple points. What do you mean by triple points? Triple point is that region of that point in the phase diagram where 3 phases are in equilibrium. Is it not? So, okay, fine. Now let us see where are the triple points in this diagram. Look at this point. This is the point. Which are the phases in equilibrium? One is rhombic, monoclinic, and vapor, sulfur vapor. This is one triple point. In fact, these triple points were labeled with some were shown as dots here in this diagram. Anyways, one triple point, second triple point, third triple point. First, B is a triple point here, C is a triple point here, E is a triple point here. Okay, so what is that we have to do now? We just have to, in any phase diagram, describe which are the phases existing along these curves at the triple point inside an area. Which are the areas now? A, B, E is one area, A, B, E. B, C, E is another area. G, E, C, D is one more. A, B, C, okay, A, B, C, D. A, B, C, D. A, B, C, D is the last one. Fine. Now, this is okay. I'm showing you a phase diagram and asking you to, and making you understand. But in exams, you may have to sketch the phase diagram all by yourself without looking into anything, of course, without looking into anything. Now, I will tell you simple steps to construct, easy steps to construct a phase diagram. First, of course, the shape of the phase diagram you have to memorize. You have to understand. You should read and understand. First, you write the areas of. Means in this phase, how many areas? Write it as rhombic sulfur. monoclinic sulfur, liquid, vapor. So once you write these phases enclosed in an area, rest becomes easy. Okay. All that you have to do is how to describe a curve now. Now let us take AB, AB, AB. What is AB? AB is nothing but how does a curve appear in this phase diagram? What are the physical significance of these lines, curves in the phase diagram? AB is the sublimation curve of rhombic sulfur. Is it not? That means along AB, you take a point on AB, and that point has two values, right? Two coordinates. One is pressure, one is temperature. So you take a point here, for example, here, corresponding pressure and corresponding temperature you take. At those 2 points, at those two values of pressure and temperature, there is a transition from rhombic to vapor or vapor to rhombic. So these two phases are existing. If you have any other value go inside the area, only rhombic exists. Any other value come here, vapor exists. Along this line, the transition from rhombic to vapor happens. So this is nothing but the AB is the sublimation curve of rhombic sulfur. Is it not? Okay, fine. What is BC? What is BC? Now let us explain curve wise. What is AB? Sublimation curve of rhombic sulfur. What is BC? BC. BC is sublimation curve of monoclinic sulfur. Is it not? Sublimation curve of monoclinic sulfur. See here, along BC, the monoclinic sulfur sublimes into vapor. I hope you understand sublimation term. That is direct conversion of solid into vapor without going through the liquid phase. What is the usual transition pattern? A solid becomes liquid and then liquid becomes vapor as you heat it. But sublimation is direct conversion of solid into vapor. And what is the CD? CD curve. This is the CD curve, where liquid is converting into vapor. It is nothing but the boiling curve or the vapor pressure curve of liquid sulfur. Boiling curve is also called vapor pressure curve. Vapor pressure curve of liquid sulfur is CD. Now, okay, AB, BC, CD, CD. What is BE now? BE, a straight, almost a straight line going vertically upwards. So almost vertically upwards. So what is this? This is the transition curve for rhombic and monoclinic sulfur. Is it not? You just take the phases which are lying on either sides of this line. That's it. And the change between them happens along this line. So you take any pressure and temperature value along this line, two phases will be in equilibrium. Any other value, only one phase will come. Either this side or this side, only one phase will come. Only along these values of pressure and temperature, there is an equilibrium between rhombic and monoclinic sulfur. That's the meaning of any curve in any phase diagram. Only along this curve, or all the temperature and pressure values lying on this line, the equilibrium between the phases are existing. Okay, so that is BE. What is CE? This is the next curve. What is the CE? CE. It's the melting curve of monoclinic sulfur. Okay, it's the melting curve of monoclinic sulfur. What is, because monoclinic sulfur is getting converted to liquid, CE. You see, you consider a curve, you consider the curve CE and see which are the phases on either side of the line. One side it is monoclinic sulfur, the other side it is liquid sulfur. So this is melting curve of sulfur, monoclinic sulfur. And the last line EG. EG. Okay. See, what is there? This side, rhombic sulfur. What is there? This side, liquid. So EG corresponds to melting curve of rhombic sulfur. Okay. CE is the melting curve of monoclinic sulfur. EG is the melting curve of rhombic sulfur. Okay. So these are the ways in which we should identify the curves and explain them, curves. Now, that's one point. Second point is, how many degrees of freedom are there for this curve. Is it not? That is what the importance of phase diagram. Even without Gibbs phase rule, you can construct the phase diagram. Fine, no problem. But what is the importance of Gibbs phase rule? Given any point and knowing the number of phases along the over that point, around that point, you can calculate the number of degrees of freedom. Is it not? So let us see curve AB example. Curve AB, how many phases are here along this curve? Two phases. Rhombic sulfur vapor, sulfur vapor. So apply your phase rule. F is equal to C minus P plus 2. C is 1 because it's a one component system we are discussing. Sulfur is a one component system. Like water, it is a one component system. Minus 2, number of phases, P 2. Why 2? Because that's what we are talking about. So, rhombic sulfur and vapor sulfur. Sulfur vapor. So plus 2. 1 minus 2 plus 2 should be 1. It is monovariant. So what do you mean by that? Monovariant? It has 1 degree of freedom. That means, what is the physical meaning of that? 1 degree of freedom. You take any, you keep any one of them constant, the other will become a variable. That means at constant pressure, at constant pressure, temperature will be the variable. So over a range of temperature at a given pressure, this that means, see, monovariant, 1 degree of, that means one variable has to be specified. Any one variable has to be specified for the existence of two phases. One variable has to be specified for the existence of two phases. Okay, fine. Any curve for that matter, any curve A, B, B, C, C, D, they are all monovariant because the same formula you are going to apply. Number of phases will be 2. For any curve, number of phases will be 2. In fact, in any phase diagram, a curve is always monovariant. Even in water, we saw this. A curve is monovariant. Okay, fine. Now let us explain. So I have just listed out different curves. Whatever I explained, I have just written here. Curve. Now we will come to triple points. Fine. Okay, so what are these triple points? Where are these triple points? First of all, you look into the phase diagram and pick a point, example B, where 3 phases are meeting. B, which are the phases which are in equilibrium? At B, which are the phases which are in equilibrium? Rhombic sulfur, vapor, monoclinic sulfur. So these 3 phases are in equilibrium at B. So B is a triple point. E is also a triple point. Why? Because 3 phases are existing here. Which are those 3 phases? Rhombic, monoclinic, liquid. Along E, this is the rhombic sulfur phase, monoclinic sulfur phase, and the liquid phase. 3 phases are in equilibrium. At C, again a triple point. Which are the phases equilibrium? Monoclinic sulfur, liquid sulfur, vapor sulfur. Okay, this again there. So there are 3 triple points for sulfur system. That is what I have just written. 3 triple points, B, C, and E. And as always, like in water, a triple point is non-variant. Why do you mean by triple point is non-variant? Because apply the Gibbs phase rule. F is equal to C minus P plus 2. Number of components is 1. Number of phases is 3. And then plus 2. So that will be 0. So so the system at